everyone, thank you so much for clicking onto the video. Today's learning objectives are to firstly know that chromatography separates components of a mixture between a mobile phase and a stationary phase, and to be able to calculate RF values from a one-way chromatogram. We're then going to know that HPLC, or high-performance liquid chromatography, and gas chromatography are types of column chromatography. They separate substances because of different retention times in the column, and they may be used in conjunction with mass spectrometry in applications such as forensics or drugs testing in sport. So now we're going to talk about chromatography. Now, chromatography can be used to separate and identify the components in a mixture. And separation depends on the balance between solubility in the moving phase and retention by the stationary phase. And chromatography describes a whole family of separation techniques, and they all depend on this principle that a mixture can be separated if it is dissolved in a solvent, and then the resulting solution, now called the mobile phase, moves over a solid, which is the stationary phase. So we're going to look at three types of chromatography. The first is a thin layer chromatography, which you've already seen, but we're going to quickly review. And this is where a plate is coated with a solid, and the solvent moves up the plate. And the second type of chromatography we're going to look at is column chromatography. And this is where a column is packed with a solid and a solvent moves down the column. And then the final type of chromatography that we're going to look at is gas chromatography. And this is where a column is packed with a solid or with a solid coated by a liquid, and a gas is passed through the column under pressure at a high temperature. And so the first few things that you need to know about chromatography is that we have the existence of a mobile phase and a stationary phase. So the mobile phase is what carries the soluble components of the mixture with it. And so we have the rule that the more soluble the component in the mobile phase, the faster it moves. And we say that it's got a higher affinity for the mobile phase. And the mobile phase is usually the solvent. So if we were going to look at paper chromatography, for example, the mobile phase would be the solvent because that's what carries the soluble parts of the mixture up the paper. And so if it's got a higher affinity for the mobile phase, or if it's more soluble, the component, then the faster it moves, and so the higher up the piece of paper it will be at the end. And when we look at the stationary phase, this will hold back the components in the mixture that are attracted to it. And so the more affinity a component has for the stationary phase, the slower it moves with the solvent. And that's because it's more attracted to, so if we were looking at paper chromatography, then the stationary phase would be the paper because the paper is not moving. And this is what's slowing some components in the mixture down and not letting it move with the solvent. And so that's why we have that if we've got higher affinity for the stationary phase, then it will move slowly, more slowly with the solvent. And so at the end, it won't be as high up the paper as other things. And so a particular component in a mixture can be identified by what we call its retention factor value, or its RF value. And this is fixed for a component in a mixture where the chromatography is performed in a specific way. And one really important thing to know is that the RF value for a particular component will be different depending on which solvent you use. Now I'm going to revisit thin layer chromatography. So thin layer chromatography is a development of paper chromatography, and it's where the filter paper, which we would use in the paper chromatography, is replaced by a glass, metal, or plastic sheet. And this is coated with a thin layer of silica gel, which is also silicon dioxide, or SiO2, or it can be coated with aluminium oxide instead. And this acts as the stationary phase. And when we have this glass, metal, or plastic sheet coated with the stationary phase, we often call these plates. You'll also need to know the advantages of TLC over paper chromatography. And the first is that it runs a lot faster. The second is that smaller amounts of mixtures can be separated. The third is that the spots usually spread out less. And the last one is that plates are more robust than paper. When the chromatogram has run, the position of colourless spots may have to be located by shining ultraviolet light onto the plate or by chemically spraying the plate with a locating agent. So we use ninhydrin. And this reacts with the components of the mixture to give coloured compounds. And ninhydrin normally turns the spots purple. So this is how we can actually see them on the plate. And after the plate has been run, an RF value is calculated for each component in the mixture. And this helps us identify the components because we can compare them with known RF values of pure components using the same solvent. So what we do is we have a plate and we have the mixture, and we drop some of the mixture onto the plate and then put the plate into a solvent. And then the solvent will move up the plate, and depending on if the components have a higher affinity for the moving phase, so the solvent, or the stationary phase, which is the silica, we can see what the RF value is by calculating the ratio between the distance moved by the spot and the distance moved by the solvent. So that's how we work out the RF value. The RF value is worked out by dividing the distance moved by the spot by the distance moved by the solvent. And so then we can compare this value with known RF values for pure components using the same solvent, and that's how we can identify them. So for example, if we had done a TLC experiment and obtained this, if we were to find the RF values of the components from this, and so what we would do would be firstly calculate for x. So we have the distance moved by the spot, and one really important thing to remember is that when we measure the distances, it has to be to the middle of the spots. And so the middle of the spot goes to about 0.80, and so it's this distance here. It's from the origin to the middle of the spot. And so we have the RF value is equal to 0.80 over the distance moved by the solvent. And this is where the solvent front is. The definition of the solvent front is just the distance or the place where the solvent has moved up to. So that's at 2.75. So 0.80 divided by 2.75 is equal to 0.29. And then for y, we have the RF is equal to the distance between the middle of the spot and the origin. So that's 2.15 over 2.75, and this is equal to 0.78. And then finally for Z, we do the same thing. So we have that the RF is equal to 1.70 over 2.75. And this gives us 0.62. So normally in the experiment, we would have to measure all these distances using a ruler. But for this example, all of the measurements are given to us. And so what we can conclude from this data is that first looking at the plate, we can see that Y has moved further up the plate. So therefore, it's got a higher affinity for moving phase for the solvent. And then looking at all the RF values, Y has got the biggest. And so we can conclude that a higher RF value is equivalent to having a higher affinity to the mobile or moving phase. So now we're going to talk about column chromatography, and this is the second type you need to know about. So what happens is that we have a narrow tube, which is the column, and it's packed with a powder. So for example, we could use silica or aluminium oxide or a resin, and they act as the stationary phase. We then have the mobile phase, which is the solvent. And with column chromatography, we can call this solvent an eluent. And this is added at the top of the column with the mixture. And what happens is that as the eluent runs down the column, the components of the mixture move at a different rate, and so they can be collected separately in a flask at the bottom. And more than one eluent may be used to get a better separation. because depending on what element you use, different components will have different affinities for this mobile phase. And this method has the advantage that fairly large amounts can be separated and collected. And it's used to separate a mixture of amino acids into its pure components. So on the right, we have a diagram of what it would look like. So we have the column and we have the element at the top, and in the column we have packed this powdered solid, which is the stationary phase. And so we have to label this element the mobile phase because that's what's carrying the components along. And so what we have is the components moving down the column at different rates. And so that means that we can collect some components at different times. So first we'll have the components that have a higher affinity for the mobile phase. So they'll move a lot quicker, and so they'll get to the bottom a lot quicker. And so we collect all of those first. And then next we'll have the ones which have slightly less affinity for the mobile phase and a higher affinity for the stationary phase. And so we'll collect those, and then so on until we've collected all of the different components and separated the whole mixture. Now we're going to look at high performance liquid chromatography. So this is actually a refinement of column chromatography, but there are a few differences. So firstly, the solvent is forced through a metal tube under high pressure instead of being allowed to pass through by gravity, which is what we have in column chromatography. And also the particle size of the stationary phase is much smaller, and so this gives us a better separation of all the components. Thirdly is that the sample is injected into the column, and the components are detected after passing through the column, usually by their absorption of UV radiation. And the whole process is automated, and the results are quickly available on the computer screen. When each component reaches the detector, a signal is displayed on the computer screen, and retention times are obtained. And the retention time of a component is the time taken from injection to detection. And it can depend on the nature of the solvent, the pressure used, and also the temperature inside the column. And we can use these retention times to identify the components by comparing them to the retention times of known components. And now we're going to look at the last chromatography technique that you need to know. So this is gas liquid chromatography, or gas chromatography. So this technique is actually one of the most important modern analytical techniques. And the stationary phase that we use is a powder which is coated with oil, and this is either packed or coated onto the inside of a long capillary tube. And this tube can be up to 100 meters long and less than half a millimeter in diameter. And the mobile phase is usually an unreactive gas, and examples of unreactive gases are nitrogen or helium. So what happens is that after injection, the sample is carried along by the gas, and the mixture separates as some of the components move along with the gas, and some are retained by the oil, each to a different degree. So the components which move along with the gas have a higher affinity towards the gas, so the mobile phase, whereas the things which tend to stay behind and are retained by the oil have a higher affinity to the stationary phase, and so they get left behind. And this means that the components leave the column at different times after injection, and so they have different retention times. So with gas chromatography, instead of working out RF values for the different components, we actually use retention times to identify them. And so the components which leave with a quicker time are the ones which have a higher affinity for this mobile phase. And so they move along with the gas, and so they exit first, compared to the components which have a higher affinity for the stationary phase, so the oil, the powder coated with oil. And so they get left behind a little bit, and so they'll exit at a later time. And various types of detectors are used, including ones that measure the thermal conductivity of the emerging gas. And various types of detectors are used, including ones that measure the thermal conductivity of the emerging gas. So how we analyze it is that we get a graph that looks like the one on the right. So we have the signal from a detector, and then retention time, on the x-axis. And so the area under each peak is proportional to the amount of that component. And so, for example, we can see that this peak here, it's got quite a large area under the graph. And so that means that we've got quite a lot of that component. And in some instruments, the components are fed directly into a mass spectrometer, infrared or NMR spectrometer for identification after all of the components have been separated. And this whole process is automated and also computer controlled. And as I said before, the identification of a component is done by matching its retention time. And this is with a known substance under the same conditions. And this is then confirmed by comparing the mass spectra of these two substances just to make sure that they match. And then finally, you'll need to know about some of the advantages of gas chromatography. So the first is that it's extremely sensitive, and then it can also separate minute traces of substances in foodstuffs. It can also link crude oil, which is found on beaches, with its tanker of origin by comparing oil samples. And it's actually best known for testing athletes' blood or urine for drugs. So on the right, we have a diagram of how gas chromatography would work. And so we have the long capillary tube, which has the stationary phase. So it's got that powder coated with oil. And so we've coated that along this whole tube. And then we've also got this carrier gas, which has gone into this tube. And so this acts as the mobile phase. So we have our mobile phase here. And we have the stationary phase, which is all throughout the capillary tube. And then the sample gets injected at the top here. And so it goes in this direction. So it goes down, and depending on whether it's got a higher affinity for the mobile or the stationary phase, it has a different retention time to another component. And so all the components get separated because some will have a higher retention, a higher affinity for the mobile phase, so they'll have quicker retention times, whereas the ones which have a higher affinity for the stationary phase, a larger retention time. And so at this detector here, this is where we obtain this graph of all the components and their retention times. And then we can compare retention times with, and then we can compare the mass spectra of this substance with the substance we think it is. So now we need to look at HPLC-MS and also GC-MS. And so first we need to know that HPLC and GC, so high performance liquid chromatography and gas chromatography, are both very useful for separating small quantities of components in a mixture. But they're not as good at identifying them. And this is partly because it's very difficult to control all the variables. So for example, we have what solvent we use, the pressure and the temperature, and also because different substances might have the same retention times. And because the main way we identify components is by comparing with known retention times, if different substances have the same retention time, then we can't tell the difference between them. And we need the result of chromatography methods to be exactly correct, for example, when providing forensic evidence and also when testing athletes' blood for drugs in sport. And we can combine either of these two techniques with mass spectrometry. So we have high performance liquid chromatography mass spectrometry or gas chromatography mass spectrometry. And we do this in order to obtain information about the structure of the compounds. And how it works is that a mass spectrometer is used as the detector for a gas chromatography system or a high performance liquid chromatography system. And as each component of a mixture comes out of the high performance liquid or gas chromatography column, the time it's taken to pass through the column, so its retention time is noted. and each component is fed automatically into a mass spectrometer, which enables a compound to be identified either by its fragmentation pattern or by measuring its accurate mass.